Chapter 12, Section 12.6. We're going to label various substances with the strongest intermolecular forces that may affect their physical properties. We're going to compare and contrast relative strength of intermolecular forces to boiling point, vapor pressure, surface tension, volatility, etc. So you need to know what are the main types of intermolecular forces, and these are specifically with covalent compounds only. So London dispersion forces, everything has this force. Covalent, ionic, no matter what, everything has this force. It's due to the movement of electrons. So as long as a substance has electrons present, then it has a London dispersion force. Dipole-dipole forces are only found in polar covalent molecules. And this, you know the molecule is polar when it has lone pairs present on the center atom, or there are different domains surrounding the atom. And then hydrogen bonding is when you have a hydrogen directly attached to a nitrogen, an oxygen, or a fluorine. Directly attached or bonded is the key there. And then one more thing, there are forces known as electrostatic attractions. And at the end we'll mention this again, but I want to go ahead and state now that electrostatic attractions are a type of intermolecular force, but are only found in ionic compounds. So ionic compounds only. So let's identify substances that would have only London dispersion forces. Noble gases only have London dispersion forces. Diatomic elements have only London dispersion forces. And I do want to draw these to make a point. The reason that diatomic elements only have a London dispersion force is because they are all nonpolar, and they're nonpolar because these atoms, if they are having a tug-of-war in the electrons between them, no one is winning because they have identical strength. So all of these compounds are considered nonpolar because it's a bond between two identical atoms, and so no one is winning the proverbial tug-of-war. And I do want you to have a general idea of what most of these look like. Any of the halogens have a bond with 3 pairs of electrons around them. Oxygen is going to have a double bond with 2 pairs on each oxygen. Nitrogen is going to be a triple bond with 1 pair on the end. And hydrogen is just a single bond with no pairs of electrons around the hydrogen. So chlorine, bromine, and iodine and fluorine all look the same. And this is just chlorine and bromine. You would draw fluorine and iodine in the same exact way. Any hydrocarbon made up of just carbons and hydrogens, no matter what number of carbon and hydrogens, will only have a London dispersion force because they are nonpolar molecules. So C2H6, C3H8, C8H18, C6H12, all of these are considered nonpolar and have only a London dispersion force. And just to show you what they look like, I will draw C3H8, and it's a chain of carbons, and each carbon has 4 bonds around it. And so you'll notice it's a very symmetrical structure, which is a big reason why it's considered nonpolar. So London dispersion forces, all of these have London dispersion forces, but what's really important about this slide is that these substances have dipole-dipole interactions as their strongest force present. So that's what you really want to focus on. Why do the following have dipole-dipole forces? So if you have a group 7 element like HCl, HBr, HI, ICl, BrCl, they're 2 bonded atoms that are not alike. And so it's going to be polar. And it's for the same reason we talked about in the last slide. If I had HCl, for example, there's a tug-of-war between the electrons going from the hydrogen to the chlorine, which means there's an imbalance. And so you have a polarity moving towards chlorine because it's the more electronegative element. Therefore, you have a dipole-dipole interaction. So if you have just 2 elements and they are not alike, then they're going to be considered polar. Group 6, I'm going to draw these substances for you, is always going to be your oxygen family element, It's got 2 lone pairs and it's going to have 2 bonds. So this is typically what all of the oxygen family members look like whenever they form a compound. They'll have 2 lone pairs and 2 bonds. And then here's the last one, 2 lone pairs and 2 bonds. And the fact that there's the lone pair here is the reason why the molecules are polar. So anytime you have an oxygen family member bonded to 2 other atoms, it's automatically polar because there's these lone pairs on the center atom. If we look at group 5, then the typical arrangement will be this one, for example, pH3 is going to be phosphorus with the 3 bonds, and it's going to have 1 lone pair at the top. And if you're not sure why there are lone pairs present, it's because you have to have an octet. So there's 2, 4, 6, and we need the 2 pairs to make 8 for an octet around phosphorus. So because we have this lone pair right here is what causes this to be considered a polar molecule as well. And if it's polar, then it has dipole-dipole interactions. The last one's group 4. And this is really going to be about the bonding domains because carbon never has lone pairs around it. So if you have a carbon that has an imbalance or unlike bonded domains, so here I have 3 chlorines and 1 hydrogen. So since this hydrogen is different from the other 3 bonded atoms, this is going to be considered a polar molecule. And again, it's because you end up with an overall polarity because I have a pull going between hydrogen to carbon. I have a pull going from carbon to the chlorines, and so overall there's a dipole moving in this direction this way. Okay, the following are examples that have London dispersion forces, dipole-dipole forces, but more importantly they have hydrogen bonding. And so we're going to say that hydrogen bonding is the strongest force found in the following. So group 7, you have HF, and we already said on the last slide that this would be considered dipole-dipole because it's 2 different elements bonded, and so they'll be polar. However, what's more important is that it's got hydrogen bonding because you have a hydrogen directly bonded to fluorine. Water also has hydrogen bonding, and again, it's in the oxygen family, so it's oxygen with 2 pairs of electrons and it's 2 bonds. And it's polar because of the lone pair, but more importantly, because it's an oxygen directly bonded to hydrogen, it has hydrogen bonding. And then NH3 of the nitrogen family, it is polar because there's a lone pair on the center atom, but more importantly, hydrogen bonding is present because you have a nitrogen directly attached to hydrogen. And then finally, our last example will be an alcohol, and I'm going to draw this one for you. It's a carbon chain of 2 carbons, and then you have 5 hydrogens, 1, 2, 3, 4, 5. Put my hydrogens. And then you have this OH group. This OH group is very important. It's what makes this compound known as an alcohol. And because it's an oxygen, which is going to have 2 pairs on it, and because it's an oxygen directly bonded to hydrogen, this is going to have hydrogen bonding as well. And something else to note about this compound, which we'll see in another chapter, is that you have 2 parts to this compound. A polar side, and the rest of this, remember what we said about hydrocarbons, when you have a bunch of carbons and hydrogens, that they are nonpolar. So this is a unique compound because it has both a polar and nonpolar side to it. But for this chapter, for now, because it has hydrogen bonding, we're going to go ahead and categorize it under hydrogen bonding as being its strongest intermolecular force present. Finally, electrostatic attractions will be any ionic compound, and the key is if you see a metal and a non-metal, then it's ionic. So metal, non-metal, metal, and non-metal. It's ionic. To summarize, here's the chart. If it falls in London dispersion forces only, then it's the weakest intermolecular force. And then it's stronger as you get towards electrostatic attractions. So forces are strongest over here. And as a trend, as you go from left to right, Boiling points and melting points are the lowest for London dispersion forces only, and they're the highest if you have electrostatic attractions. And then vapor pressure is high when you have London dispersion forces only, and low when you have up to electrostatic attractions. So you'll be asked to compare elements to one another and identify, are the forces stronger or weaker, and then what does that mean about their boiling, melting points, and their vapor pressure.